So this is math 408, L function sphere packing. Because we were talking about Star Trek and Deep Space Nine, the greatest, I think, of all the shows, I will talk a little bit about my favorite character, Garrick. I had not planned to say this, and just the perspective he gives you on life. And so it's not known for a long time if he was a member of the secret police, secret agencies of Cardassia. Eventually you realize it is, but in the beginning he's always this mysterious character, and his human friend Dr. Bashir is just sick and tired of the lying. And so there's an episode where he lies about everything, and at one point you realize he's talked about how this person named Elam was responsible for all these bad things. And eventually you realize that Elam is his first name. And he's just, is there anything you ever tell me that's true? And so the doctor, in a fit of just anger, yells at him and tells him the story of the boy who cried wolf. Does everybody know the story of the boy who cried wolf? Okay, so at the end of the story, the doctor goes, and you can see, of course, the clear moral of the story: you should not lie. And Jack goes, my dear good friend doctor, that's not the moral I draw from this at all. And Dr. Bashir goes, well, what do you mean? There's no other possible. What possibly could it mean to you? You should never tell the same lie twice. A very, very interesting character. All right, so today's lecture is going to be a little bit different. So as a professor, you have a couple of options. One is to come to class prepared and ready to lecture. The other is to blow it off. I've chosen the latter, but I've chosen it deliberately. And the reason I've chosen it is because this is a senior seminar. One of the things that is problematic, and I got this quote from Serge Lang, I'm not sure if he originated it, it is unfortunate that a book must be totally ordered along the page axis. And when you're reading a book or a paper, there's this natural progression. Well, of course we do this, and it's followed by this, and it's followed by this, and it's followed by this. And you lose a lot of the sense of the discovery. Sometimes that's not a problem, but sometimes, especially when there's more than one way to go, it is a bit of an issue. And it might be better to just see, can we do it ourselves? And so I thought, rather than preparing the lecture on how to prove that among lattice packings the hexagonal is best, let's just prove it ourselves from scratch. We have a hint. What is the hint?
That it's the best.
That it's the best. So we actually know this theorem exists. So let's think, how would we actually try to prove this theorem? If we get into enormous trouble, what do we do?
Get some hexagons.
One is give up, one is get some hexagons.
Maybe look for help somewhere.
Well, yeah, I mean, one is to look for help. You can look online. You've got to be a little bit careful with online resources, but there's a lot of things you could do. The other thing is to think harder, is to just pause and come back to it on Monday. I think we'll be able to do it. The hexagonal proof I don't think is too bad. The difficult proof is that no matter what packing you have in the plane, the hexagonal is best. But among all lattice packings, the hexagonal packing is the best. So let's try to prove that. Proof among lattices, hexagonal is best. Okay, how do we start? Yes?
Define lattice.
Excellent! You start with the definition. Define a lattice. If you look at any of the results from Calc 1, let's prove the product rule, the chain rule, the quotient rule, you always begin with the definition of the derivative. So what is a lattice? Or, what is a lattice going to be to us? A lattice will be a set of points in hexagonal structure, such that. Okay, if you choose that, this is not going to be a difficult theorem to prove. So how do we define a lattice in the plane?
Well, don't really have a strict definition, but intuitively I think of it as like something that, like a small region, and it just repeats itself over and over again.
Okay. So if I continue and try to make this work, would that work for you? And we can have those beautiful Escher pictures of these shapes that fill up So the repeating itself is a key part. So there's got to be some kind of repeating going on.
Gotta be regular.
So it's got to be regular. What does regular mean?
Are we just taking periodic tiling? Like, I mean, by regular, maybe you can mean something like there exist two distinct directions of translation.
Okay, so good. Now we're talking about two distinct directions. So we have two directions. What kind of objects is the lattice? What's the lattice made out of?
Parallelogram.
Is the lattice made out of parallelograms?
Polygons.
Polygons? Points?
Yeah.
What is your lattice? For me, I think the lattice is the points. And then you can connect those points and form a polygon. So, two directions, set of points. So maybe we have vectors v1 and v2, and the lattice L is the set of all numbers of the form, let's do a1 v1 plus a2 v2. And where do the a's live? In the integers. Is this a good definition for us for our lattice? I'm happy. What is the most important logarithm in all of mathematics?
Natural.
Nope. The W log. Right? The W log is the most important logarithm. Without loss of generality. Simplify the problem. I talked to you about Morley's theorem. Without loss of generality, one vertex is at 0, 0, one is at 1, 0, and the other one is up here. Can you do any simplifications to this lattice to make things nice?
Make one of them the unit vector?
Good. Which one is the unit vector?
Actually, the first one.
Of course the first one. The second one, please. V1 will be 1, 0. And again, this is starting to help us. So as a hint, when you are doing your proof of Heron's formula, be very careful that if you are drawing a triangle and you're dropping lines and whatnot, that those lines actually have the properties you want. Depending on how the triangle is oriented, you may not have that. If I drop the perpendicular from this point to this side, it actually doesn't hit inside the triangle. If I dropped it from here, however, it would. And so you want to be very careful if you are using an image that you do not subtly assume properties because of how you've drawn the image. What can we say about the second point? So we know the lattice is beginning to look like this. Bunch of equally spaced points. What can you tell me about V2? Yes?
Does it need to have unit length, or can we bound its length by some value?
So if V2 has unit length, then that forces me to have the two directions of the same size.
Yeah.
So do you think we have the ability to do that, or do you think that that is an extra assumption? That's an extra assumption. So we cannot assume V2 has unit length.
But we can bound it, maybe.
We can. What can you tell me about the length of V2? You have some freedom here.
At most one.
I'm sorry? Good, it's at most one, because we could say, look, let's take whichever vector is longest, call that V1, and then just lean back. And so now we put the x-axis in that direction. Linear algebra is all about finding the right orientation. If I give you the equation of an ellipse, x over a squared plus y over b squared equals 1, this is just an ellipse in the standard orientation. This is a, this is b. If I decide to give you an ellipse like this, you probably haven't done this in high school, probably because your teachers have better artwork than I do. Let's try and do it a little bit better. But if I change my coordinate axes, uv instead of x and y, in the new uv coordinates, it has the same definition. And so I could actually write this as the matrix 1 over a squared, 0, 0, 1 over b squared, xy equals 1. This is another way of writing the equation of an ellipse. I would get something very similar in UV space. And I can use a rotation matrix to rotate from xy to UV. So I will not assign this as a formal homework problem, but you should know how to write down unofficial write down the equation. And this is essentially the main idea of linear algebra. Choose the coordinate system that is good for the problem. And so when we're doing this, we might as well say whichever vector is longer, and if there's two, then it doesn't matter, choose that to be the unit length vector, and then the other one has a smaller length. Or a length that's the same. I yelled at somebody, I think, for saying positive when it should have been non-negative. V2 could have the same length as V1. But now we can assume that it can't be shorter. I'm sorry, that it can't be longer. We can do that level. Okay. Can I erase ellipses? Okay. So we know the length of V2 is at most 1. What else can we assume about V2 for convenience? Yes?
Maybe it's in the first quadrant.
Can we assume it's in the first quadrant? So give me a weaker statement than it's in the first quadrant.
The upper half.
It's in the upper half. Because if it was in the lower half, I could replace V2 with negative V2. So I can assume V2 is in the upper half plane, H. So now we want to see if we can go from that to it has to be in the first quadrant. Yes?
We could say V2 is V1 plus V2.
Good. So what we could then do is, if it's not in the first quadrant, we could keep subtracting, right? But if we do that, could we change its length?
Yes, but it'd still be less than 1. Right. But
Would it?
no, never mind.
So now it gets interesting. Which do you think it matters more, that its length is at most 1, or that it's in the upper right quadrant? Upper right quadrant. So I think we're willing to say we'll get rid of both of these and say, without loss of generality, V2 is in the upper right quadrant. Yes?
I don't know if this is useful, but I believe we still have a bounded root 2 for its length.
Could be. But now that, I'm going to claim that it doesn't matter anymore. Once I know that, here's V1, and maybe here's V2, can I move things now and make V2 the longer vector and have V1 of length at most that of V2? Could I play some kind of scaling game like that? Just make this the x-axis direction, and now you've got V1 in the upper right quadrant coming from V2. So when we subtract things over, we actually do lose that its length is at most 1 potentially. If it had just missed and it was length 0.99999, and then we subtract 1 over by Pythagoras, its length would be larger. And I agree from what you say, its length would be at most square root of 2. So we could say its length is at most square root of 2, Or we could say, if necessary, just shuffle things around again, and now when we do it, we can assume that its length is at most 1. Yes?
Oh, wait, when we do it again, then, like, how do we know that the other one will be in the upper right quadrant?
Well, just because now if we make this the direction, and just, flip things around, you might have to do some flips.
Oh, I guess if we're allowed to do flips, can't we just, like, if it's, like, in the second quadrant, just, like, flip it?
Well, actually, I guess, yeah. I mean, I guess if it's in the second quadrant, the easier way to do it is to just flip V1.
Yeah.
And if we flip V1, then V1 and V2 are both in the second quadrant. And then what we can do is just then flip that whole thing.
So I guess with enough flips, we can make it.
Right. And again, this is a function of not having prepared the lecture. Okay? But I think this is more informative because we know the result. Let's talk about the thought process. The goal is not for you to read textbooks for the rest of your life. If you think that this is mathematics, you have been misinformed. Unless you want to be an editor at a textbook series and provide scientific commentary, in which case, yes, that will be how you will spend your life. The goal is to produce new mathematics. What's more important than the theorems themselves is the thought process of how you get there. And just thinking about how would we go about simplifying things. All right, so now we have, without loss of generality, we have V1 is 1, 0. V2, we have to give it a name. What do you want to call its coordinates? You can think of 2 natural choices. XY, but I might want to keep XY free as a generic point. I would probably do either A, B, or alpha, beta. Just so that I can keep XY as a general point in the plane.
You already have your AIs.
We already have what?
AIs.
All right, so let's do alpha, beta. So V2 is alpha, beta. This is where you're thinking, well, if I'm writing a book, do I really want to have to do alphas and betas? Yeah. I do /GA for Greek alpha in my text shortcut code, so I don't have to write out the whole word alpha. And after a while, you get used to your own text shortcutting. All right, so now, what we know is, let's call this point 0, 0. We have some lattice like this, if it's the special case when V2 is coming straight up at a unit length. And that's the most standard lattice that we've seen many times. So this would be 1, 0, this would be 0, 1, and this would just give us the square lattice. We want to consider something a little bit more general. So instead of having that, we would have some other point up here, and this would be alpha, beta. And then we would just translate all of these down and translate this backwards. So this is not to scale. All right, so this is the general structure. What size radius do we want our circles to have? Okay, why 1/2?
We've already picked V1 as 1, 0.
Yes, we picked V1 as 1, 0. So it seems like we should have the radius of 1/2. Do you like the idea that V1 has length 1? I see at least one person shaking their head. What would you like to do?
I'd rather the radius be 1.
You'd rather have the radius be 1.
I don't want to square 1/2.
Right. So what are you going to do?
I'll make V1 2, 0.
So there is a great episode, I'll try to see how many Star Trek quotes I can throw in. There's a great episode of Star Trek Next Generation where the omniscient, powerful being Q loses his powers. But he's still trying to show that he's useful. And so there's a meteor that's about to destroy a planet. And everybody is running around, the Enterprise is trying to stop it, and Q is trying to be somewhat helpful. And so they ask him, well, what should we do? Well, just, change the gravitational constant so you don't need as much force to move it. We can't change the gravitational constant by just waving our hand. Oh, well then I don't know what to do. And then of course they wait, but if we do something with the warp field that could affect it, and then they do the technobabble. So we'll just do that. We'll just rescale the universe and make that a 2. And we'll know that alpha squared plus beta squared is less than or equal to 2. Less than or equal to 4. The very fancy 4 coming from 2. Okay, and so we're doing this so that, the idea is we want to put down a circle at each lattice point. And yes, these are circles. They look so much nicer in the book. Now, we have to have a circle over here. And, circles over here as well. What can you tell me about alpha beta? Yes.
It must be at most, alpha squared plus beta squared must be at most 4, 2.
Why at most 4?
I mean, sorry, at least 4.
Okay, because if alpha squared plus beta squared is less than 4, then that means it's too close to put down the circles. So we know it has to be at least 4. Right? Could it be more than 4?
We have that written down.
I'm sorry?
Sure, no idea.
So we know that it can't be more than 4.
Why is that written down? Because we want V2 to be smaller.
We want it, right, because you can choose one of the vectors to be the larger one. Let's choose V1 to be the larger one. And so you can see now the benefits of doing this. Yes?
I guess we're making the assumption that, the circles should be touching each other.
Well, here's the thing. Because we assumed V1 was the longer length, we now get for free that alpha squared plus beta squared has to be 4.
For the circles that we're packing, we're assuming that. I think there's still some sort of assumption that we're making that
Well, no, you are. So here's the thing. If the circles had a smaller radius, would we have wasted space? Could we just say that we could just expand the circles? Or are we making some subtle assumption here? Because maybe, depending on what this is, we would have wasted space. We might be able to lose a little bit space here and gain a little space there. So have we just made an assumption?
So the assumption feels right to me intuitively, but I think we still made an assumption.
Yes, and yes.
I mean, I think our assumption was when we said V1 is 2, 0, and they're unit circles.
Yes, and so we made an extra assumption.
We couldn't do both of those without working generality.
So it's very easy to make assumptions and not even be aware that you're making assumptions. Anybody know the joke about this word? 2 people know, 3 people know, 4 people know. Have you seen this joke?
Probably.
I learned this from an episode of The Odd Couple. When you assume, you make an ass out of you and me. And so it is very easy to have a subtle assumption floating around. Sometimes the assumptions are not subtle. So I am a managing editor of the Journal of Number Theory. We get lots of people who elementarily prove things like Fermat's last theorem. And one of my favorite proofs from, I won't say too much. So you have x to the n plus y to the n equals z to the n greater than or equal to 3, x, y, z greater than or equal to 1. And Fermat conjectured that there are no solutions in the integers. One of my mentors at Princeton, Andrew Wiles, is the one who proved it with an assist from his former student Taylor. And one of the proofs I have seen begins, let n equal phi of m, where phi is the Euler-Totient function. So does anybody know properties of the totient function? Yes?
Make only even numbers.
It takes on only even numbers. And so he's doing this analysis. And I said, well, okay, but your analysis is not going to handle arbitrary numbers like 3. Or in fact, it's not going to handle when n is a prime. And in fact, it's sufficient to just do this when n is an odd prime because we know what happens at 2 and 4. So you have to be very careful that we're not making assumptions. All right, so let's back up and see. So we definitely have, our points down here on the x-axis. We know that the largest radius we can take is 1. But maybe we don't take something as large as 1. And now we have points up here. And so what do we do?
Do you just keep expanding the circles, or just calculate them?
So we can expand the circles until they hit.
You can also change the vectors.
We could, well, let's hope we've already fixed and located where the vectors are at this point.
I think though the top circle could be lowered so that it's touching the other two, right? We don't have a lower bound on.
Right. But I think we just expand the circles until 2 of them hit.
Okay, yeah.
We don't know if all 3 will hit. But I think as long as we do that, we're fine. Because, by symmetry, whether or not this hits that is the same as if this hits that. And then is this hitting that the same as this one hitting that one? Yes.
Oh, so it is like form lines of hitting it in one of the
Right.
directions, depending on which one hits it.
So now when we look at what's going on, we have 2 possibilities. And the question becomes, what's the best way to do the analysis?
Can you just calculate the distances between, well, I guess the lengths of the vectors, but then you'd also need to calculate between like the third vector and the triangle.
Yes. So right now, this hasn't come into play yet. And at some point, the angle that this is taking should matter. As this angle comes further and further down, that's going to decrease the size of the circles we can have. So what we could do is, for every choice of this vector, we could see what's the largest circle we can draw where they don't hit. And so what lengths are going to come into play? So this length here is 2 units. This length here is the square root of alpha squared plus beta squared. And then over here, that's going to be the third one. And then we just look and see which of these lengths is smallest. And that's going to control what happens. What's going to be nice about the equilateral triangle, or the hexagonal lattice?
Side lengths are the same.
Yeah, the side lengths are the same. So it's going to be the same for all of them. So let's think about what's going on now. So here's the point 0, 0. Here's the point 2, 0. Here's the point alpha, beta. And now we need to look at the different lengths. So this is 2. This is the square root of alpha squared plus beta squared. And let's call this angle maybe theta. How do we find the length of the third side? Law of cosines. So if you don't know how to prove the law of cosines, please either look it up or try to prove it yourself. Basically, law of cosines would be, if we called this side s squared is going to be 2 squared plus alpha squared plus beta squared minus twice, minus 2, sorry, square root alpha squared plus beta squared cosine of theta. Well, actually, is minus 2?
Yeah, the two.
Yeah, I'm saying it's minus 2 times this, right?
Yeah.
Right. And so minus 2 times 2. So that gives us our side. How do we understand the cosine of theta? Yes.
We look at the right triangle with alpha and beta.
And so we can replace cosine theta with is going to be beta over the square root of alpha squared plus beta squared.
Would it be alpha?
Will be alpha, sorry. And so we get s squared is 4 plus alpha squared plus beta squared minus 4 alpha. Well, that's actually pretty nice. You know, at least the square root of alpha squared plus beta squared is gone. It doesn't look so bad anymore. Okay. What do you think happens as alpha gets very small?
That value approaches, like, gets bigger, and then,
I'm sorry?
like, that value, s squared becomes larger than the other one. Because we're just focusing on the smallest value, right?
Right, we just get, right, and we know one of the values is 4, one of the values is alpha squared plus beta squared.
Yeah.
So the question is, how small can 4 alpha be, negative 4 alpha be?
0.
It could be 0. And if that's the case, you know, we don't have the last anymore, so we could just say it's extremely, extremely small, in which case subtracting the, you know, 4 alpha is not that big of a deal. But the steeper, oh, I'm sorry, the smaller up it goes, the further out beta is going to need to be if we want things not to interfere. But we're already assuming alpha squared plus beta squared is at most 4. So this is giving us, you know, some control. So we know if alpha were the larger component than beta, and we had some idea of its size, maybe we could say, you know, something that this is larger than 4, and that the critical threshold is going to be the 2 circles touching on the x-axis. And so a lot of this comes down to trying to find what's the right picture. And as what I'm hoping you're noticing is that what you thought was the right picture at, you know, 12 might not be the same as 1210, it might not be the same as 1235. You know, that as we keep progressing, we might find this is a better way to look at things. You know, we can initially make this simplification. Let's assume this is the longer direction. Well, maybe that's not what we want to do. Maybe it would be better if this was the shortest direction of the 3 quantities. Can we do that? So we were going to have some kind of triangle like this. Can I change my vectors and whatnot so that this is the smallest of the 3 sides and just rotate things a bit? I can always rotate things so that that's going to be the smallest of the sides.
So fix it and make the smallest one instead of fixing it and making it the largest one.
Yeah.
Yeah, that way we can have like, I guess,
And then we don't have to worry about this circle hitting either of those two. It's just these 2 circles hitting each other.
So then we
Right. And then that will give us the best we can do. Does this make sense? What do you do? I have everyone's agreement? And again, have we constantly changed how we're orienting things? Absolutely. And the point is, as you start doing the calculations and you start to see what is going on, this should not excite you. If this does, you have problems. I had those problems when I was a child. And I would just do brute force calculations. And I showed you the Morley theorem, that one of my friends just had to do almost an intervention and just really drive home the point to me that you should not do a brute force calculation just because you can do it. And so now we will change. So x direction is the shortest. And so can we still assume V1 is 2, 0? Yes, so that's still true. Can we still assume V2 is alpha beta?
Yeah.
Sure, it's still in the right quadrant, that's not a problem. And here, alpha beta greater than or equal to 0. Actually, strictly greater than 0. Can we assume now alpha squared plus beta squared is?
I don't think we are strictly greater than 0. Alpha could just be 0.
Yes, you're right. Alpha could be 0. Alpha plus beta greater than 0. Alpha times beta greater than or equal to 0. Is that enough? Because if one of them is negative and the other is positive, then this would fail. I think that might be a nice way to phrase it. I'm not 100% sure, but.
I'm just gonna say alpha greater than or equal to 0.
Right, and beta greater than 0. That's that's a better way to say it, but I was trying to be funny. Alpha greater than or equal to 0, beta greater than 0. What about this? Alpha squared plus beta squared less than or equal to 4.
Greater.
So now it's
Greater.
greater than or equal to 4. And in fact, with the equilateral triangle, it could actually be exactly equal. Okay, so hopefully this picture will now work. And then we have some other point over here, which I'll just draw a little bit higher up just to really emphasize. And then, drawing my circle like this, drawing my circle like that. Let me get here. Something like this now. So all we have to do now is figure out what fraction of the plane we cover. Well, there should be something that's clear that we can do to make this a more efficient packing. Yeah, so there's going to be a sequence of lattices that dominate each other. All we have to do is find the best one. As long as there's a gap here, I can just shrink things down until it touches at least one of them. So without loss of generality, shrink or push down till touches at least one circle. Later we'll talk about the kissing problem, or the, well, that's a good phrase. If you have a circle, how many circles can touch it? In 1 dimension it's easy, in 2 dimensions it's easy, 3 dimensions was finally proven, but only in the past 100 years. Conjecture goes back to Newton. But I believe it's 12 that you can do in 3 dimensions.
Oh, of the same size.
Of the same, right. And when you have higher dimensional spheres, it's only known in very special cases what the largest number of touching spheres you could have where they all touch one common sphere. So now, how do we figure out what fraction is covered? Yes?
Break the plane into parallelograms.
So break the plane into parallelograms. And so, I tried to choose, something nice over here. And we would want to know how much is covered in each one. Yes?
I think we can actually say that rhombus
They should be. Yes, because these will be parallel sides to that, and those will be parallel sides. Rhombuses, wait.
Yeah, right?
So wait, what's the definition of a rhombus?
All four sides are the same.
All four sides are the same.
Because from the pushing down, we get to the triangle as isosceles, right?
I mean, if we know that would be good. So as it pushes down, is it possible that it could touch this one but not that one? Are you saying that it has to touch both?
Well, because the top
No.
two touch each other, like the.
One of them has to touch.
So okay, so these two touch and these two touch. So we do know that this side is the same as that side.
Yeah.
Yes, good, excellent. So we know we have a circle coming here, and a circle coming here, and a circle from here touching, say, this one.
Yeah, then by symmetry, the rest of them.
So really poorly drawn, like that. And so I should be drawing the lines this way, maybe. So this would be,
We can pick the pair we choose.
we can pick the pair we choose.
Isosceles, so
Yes.
that they're rhombuses.
And then
Well, by symmetry,
these two
other
sides are
two
going to be the
must
same.
touch, like, the one in the top right corner also has to touch the other two, because it's symmetrical.
So this has to touch that one?
Like the top right point, there's another circle,
Yes.
fourth circle, and that one has to touch it at the same point.
So it will touch this one, but does it have to touch this one?
Yes, because the first one touches that one by symmetry. Because
Yeah, it does.
yeah, like the top left and the bottom left touch.
Okay, okay.
Top left doesn't have to touch both, though.
Right. This doesn't have to touch both, but this will. But wait, if this one touches this one and this one, then all three touch. So if you know, so do we know? Yes.
No.
Yes.
So, well, I was just gonna say, like, I guess regardless of how they touch or whatever, like, it should just be one unit circle inside the rhombus.
Well, we have it coming from four different places.
Because
By how things go. So
yeah,
is it
like
just
this whole
one?
area is
Good.
just one unit circle, because it's like pieces of pie that add up to 360 degrees.
So when you look at this part over here is the same as this over here.
Mm-hmm.
And then this part over here, so, let's see. So here, if I'll call this 1, 2, 3, and 4. So this over here is the same as 2.
Yeah.
And then this 4 over here is the same as this over here.
Yeah.
So this is 4. And then this poorly drawn over here, that's going to be 3.
So I think we can just figure out the area.
So all we have to do now is figure out the area of the parallelogram. And so this is really nice by the tiling. Do we need them to actually be kissing now? Or would that just decrease the efficiency? Would that just increase the area of the parallelogram?
Wait, you're kissing as in three of them?
Or just at least 2 of them kissing?
Yes.
This statement is still true if they're not kissing.
Yeah, like,
But when they're kissing,
You know it's more efficient.
yeah,
Correct.
but like,
But this statement is true independent of them kissing.
yeah.
I mean, we just have to be careful because we have so many assumptions, right? This is why you do the argument first and then you write it up nicely afterwards. So a lot of the assumptions we made, we don't really need. In particular, I don't think we're going to be using this at all.
We just need to minimize the parallel.
We need to minimize the area of the parallelogram. So what is the area of the parallelogram? So we have the vector 2, 0 over here, and we have the vector alpha, beta here.
But it's a rhombus, right? So
It's
the
a
sides
rhombus.
are all like 2.
I'm sorry?
Alpha squared.
But not all rhombuses have the same area.
The area is 2
Yeah.
beta.
I'm sorry?
2 beta
Okay, how did you get this?
based on type.
Oh, yeah.
Okay, so and that's going to just be 2 beta.
So we just need to find how we can minimize beta.
But it's interesting to think, what else were we trying to do to calculate the area of a rhombus? So my son is taking geometry right now. It would be interesting if they would have actually found this a little bit faster. There is another way. What's the linear algebra way to find the area of this?
Like
Yes! The cross product, or the two-dimensional determinant. 2, 0, alpha, beta, take the determinant of that, and you get 2 beta. Right? Yes?
Yeah.
So we've done this before. Oh, babe, this is like an overkill. But, good, I actually do prefer just base times height. So we are now really close. We want to minimize 2 beta subject to alpha squared plus beta squared is greater than or equal to 4. Something doesn't seem quite right about that.
Well, and we need to make sure the other two don't touch.
Yes.
Because they're seven.
And so if beta becomes too small, this is going to come down and touch over here.
We just need to do a distance formula from alpha beta to 2, 0 and make sure that it's like greater than or equal to 4 also. Because
Okay. So we
we
need
already know that the left hand
so we need alpha minus 2 squared plus beta squared greater than or equal to 4. So alpha squared minus 2 alpha plus beta squared is greater than or equal to 0. Just canceling the force from both sides.
Oh, but alpha squared plus beta squared is greater than or equal to 4. So you just need 2 alpha is greater than or equal to like 4 and 2 or something. Like 4 and here.
So now, since this is at least 4, we get
Yes, manipulation not easy now.
wait, so alpha squared plus beta squared is at least 4. So
Negative 2 alpha needs to be at least negative 4.
so we have 2 alpha is less than or equal to alpha squared plus beta squared.
Oh, never mind.
And so unfortunately the inequality doesn't go the right way.
2 alpha less than or equal to
Yeah, we know that this is at least 4, but since 2 alpha is less than that, this gives us no information. So we're close right now. And we have to make sure the circles aren't hitting. And the problem is, as you make beta smaller and smaller and smaller, you are going to have a hit here. So are we assuming the circle now has radius 1? Have we gone back to that?
Yeah, I think so.
So now that the circle has radius 1, the question then is, how small can you make things and not hit?
So it has to be good. Wait, don't we already know it doesn't hit based on alpha squared plus beta squared is more than or equal to 4?
Right.
It's a cross. It's a cross.
Like that's the top, like the base versus 0, 0 versus alpha beta. You know that stuff.
Right, but the area of the parallelogram is 2 beta. We want to make the area of the parallelogram as small as possible because we're getting 1 full circle. And so if we want to minimize 2 beta, why don't we just send beta all the way down to 0?
Because then we can't satisfy the other equation.
Well, if we send beta to 0, what's going to happen? So we know alpha squared plus beta squared is at least 4. So alpha is going to become at least 2. As beta goes to 0, it's going to collapse down onto this point.
Yeah.
And as beta gets smaller and smaller and smaller,
Wait, if it collapses down to
We still
2,
don't know
0,
that's
then we
a
know
one.
that the
So
we
it's
know that
2,
it's
4, then we know, because they're two isosceles triangles.
We can do very flat rounders.
So- So the question is, do we actually have to minimize, or do we now just use the fact that this is an isosceles triangle to then deduce that it is the hexagon, essentially?
How do you know it's an isosceles triangle? Because
Any round is
Well,
two isosceles
so-
triangles, right?
So this length is the same as this length.
Yeah.
And so if these two circles are just barely kissing, and these two circles are the ones that are kissing, this length has to be 2, and that length has to be 2.
I don't think you can assume that 2 and 4 are kissing, for instance. Necessarily.
Well, if 2 and 4 aren't kissing, I mean, we have to assume 4 kisses either 2 or 1.
Yeah. Okay.
And so you could possibly break it up into
That's
2 cases.
Okay.
Doesn't that depend on whether alpha is just bigger or smaller than 1? Because if it's smaller than 1, it's going to kiss the bottom left, and if alpha is greater than 1, it's going to kiss the bottom right.
Probably.
Yeah.
It's just which leg of that triangle is, which one of the side
Mhm.
legs is bigger.
What is one?
So,
Can you just say that without loss of generality, 1 and 4 kiss? Because otherwise you can reverse the orientation again somehow. For instance, you can take like your new V2 is just alpha is V1 minus V2. Like you can take that cross diagonal and make that your new vector. So you
Probably.
can say that 1 and 4 kiss without loss of generality.
I think you can say without loss of generality that it's
Yeah.
1 and 4 that kiss. If not, you just have to do the argument twice.
So then it's just isosceles, and you just need that angle to be actually it just needs to be equilateral.
Right, and so now in
The
that,
angle
well,
has to be greater than 60. So
well, if we have them kiss, does that tell us now, because we only have 1 and 4 kissing, we don't know that 4 and 2 kiss as well.
yeah, but you just need theta is greater than 60, so that the third side is at least as large as
Right.
the other two.
And then that will, so do people mind if we just go a little bit over?
Yeah, sure.
You know, so rather than, having to, start this all over again, we're so close right now. So we'll say 1 and 4 kiss. Okay, so 1 and 4 kiss. So what does this now give us? So something like this. And here's alpha beta, 0, 0, 2, 0.
So we know that those two sides are the same length. And
So we know alpha squared plus beta squared equals 4.
And the last side's the longest.
We also have alpha smaller than 1 now.
And so alpha will be less than 1.
Less than 4 equal, I guess.
Because otherwise it's going to be closer to the one over here.
Right, I think, can we just finish it by saying, so we know that the last side has to be longest, right? Because if it's shorter, then the circles overlap.
Mm-hmm.
And so we want to minimize beta, and so the longer this last leg is, the higher beta
Yeah.
it is.
Well, because the more you rotate it.
We have two legs that are the same
Right.
side, and the longer you make the hypotenuse, or not hypotenuse, but you know.
Well, so here, so this side over here, we're drawing a triangle, we're drawing a circle of radius 2, centered at 0, 0. Right?
Yeah, so your degree of freedom is theta. You can adjust
The degree of freedom
theta.
now is this angle here, theta.
But theta has to be at least 60 for it to be the longest side. So then, to minimize beta, you just make theta 60, and then you're
Right.
Or can we just say, like, because of the first equation, alpha squared plus beta squared equals 4, to max beta. Wait, to minimize beta is the same as to maximize alpha, and that is going to be something that is technically constrained.
Yeah, we just say alpha equals 1.
Good, okay, good. I like that. So we have 2 proofs. One is maximize beta, and 2, minimize alpha. And by symmetry, the minimum alpha is going to be is 1. So if alpha equals 1, beta equals the square root of 3. And now that we know that this is 0, 0, 2, 0, this is now going to be 1 square root of 3. And so this is 1, this is root 3, this is 2, 60 degrees, and there's our hexagon. So if we hadn't talked about Garrick and Star Trek, we would have actually done it in 15 minutes. And in honor of the beautiful proof, rather than doing the standard QED symbol, we will do the hexagon. All right. So this is, I think, for the most part, a correct proof now that of all lattices, the hexagon does the best. There was one little part at the end where, can we really do that without loss of generality? If not, do 2 cases. But I think if you just argue it a little bit more carefully, yes, we can keep changing our orientation. And so this is not the most efficient possible proof, deliberately not. Because I want to get you into the thought process of how do you think about something like this? How do you attack? What kind of simplifications might you want to make? And it's okay if you make the wrong one. I know a lot of people are absolutely terrified of trying anything if it's not going to work. And there's this resistance to try and explore. Try a little bit, and if it's not working, stop, backtrack, try something else. I like how many times we flipped back and forth as to how do we want to define things. One of the small projects I supervised years ago, we weren't sure when we were talking about gaps between summons. Do we include the gap from the first summoned to nothing? And just whatever that is, that's also one of the gaps? Or do we not include it? It doesn't matter in the limit, because its fraction, its impact goes to 0, but we kept going back and forth all summers to do we want to include it or not. And in the end we decided, nah, don't include it, it's just easier not to. But it meant that we had to shift things by a -1 in a lot of counts. The number of summons was 1 different than the number of gaps. And think back to the gamma function, gamma of n plus 1 is n factorial. There's a little shift there. All right, so this is a good place to stop.